I'm Mayuk, and today I'll present our work, Base Transformers, Attention over Base Data Points for One-Shot Learning. Work done jointly with Kevin McGuinness and Noel O'Connor at ML Labs and Dublin City University, Dublin. Few-shot learning task can be described as an n-way k-shot classification task where k support examples are provided for each of the n classes. And the objective is to classify all the query samples to these n classes by making use of only the support data. However, this is very hard, so most current methods make use of a base dataset consisting of many labeled examples per class, but the base classes have no overlap with the novel or unseen classes used during test time. Most recent works follow a two-stage training method where a model is trained using the many-shot base data in the first training stage. In the second stage, the support data of the test episode is used to construct a classifier that is used to distinguish between the query samples. Our method builds on top of a simple and popular baseline, prototypical networks. In prototypical networks, a prototype for each class is constructed by averaging the embeddings of all support instances in a class. Then the query samples are classified into the class whose centroid is closest to the query embedding. During the meta-train phase, episodes constructed from the base data optimize the network by SGD on the meta classification loss. An encoder pre-trained on the base data produces poor representations for the novel class support instance, especially for the one-shot case. Our aim is to construct a robust prototype for the unseen class. We have K-base instances that are similar to the support image that have robust feature representations because the encoder was trained on mini-shot base classes. So we make use of part-based correspondences to select robust spatial features from the base data feature space and aggregate these parts to construct a robust novel prototype in the one-shot scenario. In more detail, we make use of a cross-attention mechanism between all spatial locations of the support instance and all spatial locations of the closest base instances. First, the support instances pass through encoder phi to get the representation phi of xi. The class name is used by the semantic query function top k to get the closest base instances whose feature representations are obtained using phi naught, which is a fixed encoder we get after pre-training the network. Key value pairs of base instance features are obtained using two independent linear layers k and v, while the transformers queries are obtained by using linear mapping q on the support instance feature. The dot product between transformers query and key features results in an attention map between the support features and the base features. This is followed by a softmax over all spatial locations of all the base instances. The computed attention is then used to aggregate the values and a residual connection from the support features is added to get the adapted prototype. We use semantic similarity between the support and base class names to get the closest base classes and hence base instances. For mini ImageNet, LCH similarity on WordNet graph is used. For tiered ImageNet, because the class splits were made using higher up nodes in the WordNet hierarchy, we get very similar LCH similarity scores between a test class label and a base class label. So similarity between BERT embeddings of class and hypernym descriptions is used. For cub, we use cosine similarity between already available category level attributes. Training is done in two stages. First stage is a pre-training stage, which is an NB-way classification task with SimCLR loss as an auxiliary loss. SimCLR prevents supervision collapse and results in representations that contain more information than just information regarding base classes. Second stage trains both encoder and base transformer on metatask sample from the base dataset. Here we have some results on MiniMeshNet and cub dataset for two popular encoders, Con4 and ResNet12. We see consistent improvements over the state of the art in the inductive one-shot setting for both encoders. However, we do not see the same improvements reflected in the 5-shot setting. We think this could be because the 5-shot prototypes are already a good estimate of the true prototype. To investigate this, we construct support transformer, which is a variant of base transformer where transformers query is a class prototype of class C, and keys and values are the features of all support instances of C, keeping all other hyperparameters same. As the number of shots approach 5, noisy prototypes from 5 different support instances of the novel class become as good as the prototype computed using base instances queried via semantic query. We also show that base transformers is limited by the querying function by constructing an oracle querying function consisting of ResNet12 encoder trained on both seen and unseen classes in the dataset. Improving the querying function results in a much higher one-shot accuracy, especially for tiered-dimensional datasets. We plan to find a better querying function using only base class information in a future work. Here we visualize the attention maps overlaid on top of base class images. For nematode, the base transformer learns to attend to visually similar regions of jellyfish, like the tentacles of the jellyfish and the spiders, the legs of the spider. For golden retriever, base transformer attends to two instances of Gordon sitter without being explicitly trained to identify multiple Gordon sitters. Please check out our paper and code for more information. Thank you for watching.